Hello, today we're looking at topic 3.11, the secant, cosecant, and cotangent functions. So those are trig functions that we haven't looked at yet. But we're looking at these three new functions, and they correspond to sine, cosine, and the tangent function, which we have spent a lot of time learning about and going in depth about. So these new functions shouldn't be too difficult to incorporate what we already know and apply that to these new functions because these new functions are basically reciprocal functions. So reciprocal functions is tying them to one of the three functions that we already know. For instance, if we're looking at secant, then secant is the reciprocal of cosine. So that means we have the same thing for secant, we can do 1 over cosine. Cosecant is the reciprocal of sine. So cosecant is the same thing as 1 over sine. And then finally, cotangent is the same thing as 1 over tangent in terms of reciprocals. So when we look at these reciprocals, if we can make sure we connect them to the right function, then we know it's just 1 over. This does become important when we're trying to evaluate or use these in our calculator, because there is no inverse or reciprocal function for each of these. So we want to know how to properly enter them in so we don't accidentally enter them incorrectly and cause some errors along the way. So the first thing that we need to pay attention to is because they're reciprocals, then this is a fraction. And there are certain places that there are certain things we can't have in a fraction, and we can't have a denominator that's zero because one, we can't divide by zero. And when that approaches zero, then it makes it become undefined. So for secant's case, because it's 1 over cosine, cosine can't be equal to zero. In cosecant, because it's 1 over sine, sine can't be equal to zero. And if cotangent, 1 over tangent, then tangent can't be equal to zero. But tangent does have one other characteristic because when we were studying the tangent function, we also learned that tangent could be sine over cosine. So the idea of reciprocal then would mean that whole fraction is going to turn upside down. So we could also represent cosine as cosine over sine. So that one has two possibilities, but also two places when it could be undefined. So if you are applying cotangent to be 1 over tangent, well, then tangent can't be zero. If you're applying the identity of cotangent being cosine over sine, then sine can't be zero. And so that's what those reciprocal values and reciprocal functions are all about. So the first thing that you have to remember, cotangent and tangent are really easy to tie together because it's basically kind of the same name. So how are you going to keep sorted? What function does secant pair with and what function does cosecant pair with? One of them's going to pair with sine, one of them's going to pair with cosine. So I had a high school teacher that always told us every co has a non-co. And what she meant by that is you look at the prefix here. Secant does not have a prefix of co, so between sine and cosine, cosine does have the prefix of co. So this doesn't have a prefix of co, so it's going to match up with cosine, which does. And cosecant has a prefix of co right here, so it's going to match up with sine because sine does not. So if you like that memory device, use it. If not, figure out how you're going to keep them straight and you will be fine because we just want to make sure we're pairing the right function with its correct reciprocal. All right, so this graph should look familiar. When we did the tangent function, we went ahead and found the first quadrant values so that we would recognize those numbers because we learned as we were finding the tangent values, if we knew those three values in the first quadrant, then it was we could easily obtain what that value was in a different quadrant because it's going to be the same ratio, but we had to pay attention to if it's going to be positive or negative in quadrant 2, 3, and 4. So the same thing is going to be true with our reciprocal functions, cosecant, secant, and cotangent. So you might want to do this part on a sheet of paper so you can have it and add it to your notes. But we're going to work on these three angles. You should know by the time we do these three angles how you're going to do this at the different quadrantal angles, because we do know that on quadrantal angles, then there are going to be some that are going to be undefined as well. And we know that when a trig function has undefined values, then it does mean it's going to have a vertical asymptote. Okay, so let's get this going here. So on this angle, we're going to have pi over 3, and then we have pi over 4, and then we have pi over 6. So those are the angles that we've been doing. And when we first started learning this, we learned those coordinate values for pi over 6 was 1/2 root 3 over 2. And pi over 4 was root 2 over 2, root 2 over 2. And then pi over 6 was root 3 over 2, 1/2. And so what those values gave us is the cosine and sine values for each of these angles on the circle. Again, you can kind of go back to the quadrantal angles later, but we're just going to focus on these three. So then when we studied tangent, we learned that tangent is sine over cosine. So if I take sine and I divided it by cosine, simplified it down, then I got square root of 3 for the pi over 3 one. And when I did pi over 4, that was pretty easy because anything divided by itself is just 1. So that's tangent. And then here we did sine divided by cosine. So 1/2 divided by root 3 over 2 and rationalize that out. We got root 3 over 3, which is a tangent value here. All right, so we're going to do the same thing with our new functions. And so I'm going to kind of work through this first one with you so you can see, and then I'll give you a chance to pause your video and make sure you can do the same thing for the other three. So as I do cosecant, remember that that's the reciprocal of sine, so we can do 1 over sine. So we know the coordinates for sine on our unit circle are all these secant values right here. So I'm simply going to take 1 over the sine value, and that's going to give me the cosecant value. All right, so if I do this first one here, sine is root 3 over 2. So if I do 1 over root 3 over 2, that's the same thing as 1 times 2 over root 3, which is going to give me 2 over root 3. And if I'm going to get that radical out of the bottom, then I would multiply the bottom by root 3 and the top by root 3. And so what is that going to give me? That's going to give me 2 root 3 over 3. And that's my cosecant value at pi over 3 is 2 root 3 over 3. Okay, then to calculate my secant, secant is the reciprocal to cosine. So we're going to use 1 over cosine. And so when we go here to this point again, I'm going to take 1 over, and my cosine value is 1/2. So then I'm going to take 1 times, and the reciprocal would be 2. So that's just going to be 2. And so I'm going to have 2 for my secant value. And then I'm going to look at my tangent value. And for me, I'm going to do 1 over tangent. You could do cosine over sine, whichever you wanted to do at this point. Excuse me. I'm going to do cotangent, not tangent. And so how I'm going to do my cotangent, I'm going to do cotangent of x equals 1 over tan x. It's because I already know the tangent values, and then that saves me a little bit of the division, but you could come back here and say cosine divided by sine, just like the identity tells you right here, and be able to get that value. So on this one, then I'm going to say 1 over root 3 because that's my tangent value. And to get the root 3 out of the bottom, I multiply the bottom by root 3 and the top by root 3. So I get root 3 on top. And if I take root 3 times root 3, that's root 9. And the square root of 9 is 3. So my tangent value is going to be root 3 over 3, or my cotan, excuse me. Okay, so I want us to develop that number pattern so we start recognizing what cosecant values would be, what secant values would be, and what cotangent values would be for these three angles. So go ahead and pause your video and finish out pi over 4 and pi over 6, finding the cosecant, secant, and cotan values on each of those lines. So how did you do? Were you able to get those values? All right, so again, I want you to start recognizing the secant, cosecant, and cotangent values so that you can do with them exactly what we did with tangent. You know the value, then you can just decide when is it going to be positive or negative in which quadrant. And I will tell you, as we've learned, that these reciprocals will be positive and negative in the same quadrants as their other part, the sine, cosine, and tangent. So in the first quadrant, everything, all values are the same. In the second quadrant, so there is a little memory device here if you would like it. We've talked about it before, but all students take calculus or whatever acronym you want. But in the A stands for all trig functions. All 6 are positive in the first quadrant. In the second one, sine and its reciprocal, which would be cosecant, will be positive. Tangent and its reciprocal cotangent will be positive in the third quadrant. And cosine and its reciprocal secant will be positive in the fourth quadrant. So that is just when the trig function is positive. Okay. So keeping that in mind, now we're going to dig into each of the actual functions and look at their behavior. Again, we're going to look at this as graphing from the reciprocals. And because we know that whenever we have fractions, which are reciprocals often, then we're going to have vertical asymptotes wherever the denominator is 0. All right, so the first one we're looking at is secant. And these graphs, secant and cosecant, are a series of hills and valleys. So what we start with is we think about this as the sine function or or its reciprocal function, depending on which one you're talking about. So in this case, secant, remember, is paired with cosine. So we're going to create a cosine graph that runs through the middle of the graph. So when you see this dotted line, that obviously means it's not a physical part of the graph because dotted lines are guides, not actual physical pieces. And so that is the cosine graph, right? It starts up here at 0, 1, then the middle, then below, then the middle, then back up here, and you can see that valley that's happened right there. So everywhere that cosine graph touches the middle of the graph, in this case, the horizontal axis is on this line right here. So everywhere that this sine function is 0, remember, or excuse me, cosine function is 0, would be when secant is undefined. And secant is undefined where you see these vertical asymptotes. And those vertical asymptotes are happening repeatedly in the graph every time that our cosine value is 0. Okay, so there's your vertical asymptotes. And we know that we can't cross vertical asymptotes, so that means your graph is trapped between the two vertical asymptotes. All right, so these vertical asymptotes are happening again where cosine is 0, and here's the equation. So we have to have equations for our asymptotes because they repeat. So the first vertical asymptote happens right here at pi over 2, and then every pi over 2 increments from there. Well, I'm sorry, not pi over 2 pi, right? Because we would go from here all the way over here, and that's a unit of pi. So each one hops over pi units, and that k, remember, is how many times is it hopping over? What's the integer number that I can use? So if I want to jump from pi over 2 to the next asymptote, then I would do 1 times pi and add that to pi over 2. If I wanted to skip over to the second vertical asymptote from that, then k would be 2. So then I would do 2 times pi, and I would add that to pi over 2. And that's what this equation is telling us. The period, or one period of this graph, falls between the asymptotes. And it does look a little bit different because a sine or cosine graph is one hill and one valley. So for a graph like this, we would consider starting here at this vertical asymptote and going over to this one right here. So from this asymptote to this one. Okay, and that is considered one period of secant. A period of secant includes a hill and a valley. And if you look at this point right here, this point, which is the bottom of the valley, is at the top of the cosine graph. And this point right here is at the bottom of the cosine graph, but at the top of the secant graph. So once we can rough sketch our cosine wave in, then we find where these vertical asymptotes are going to happen whenever our cosine graph is 0. And then at the top of each hill of the cosine graph, we'll find the bottom of the secant. And at the bottom of each cosine, we'll find the top of the secant, and that's that relationship. So the characteristics here to start learning are that your period is 2b. The range goes from the bottom to top, so from negative infinity up to that point, including that point because that's physically on the graph. And then we jump to the bottom of the top part of the graph and go to positive infinity. So we include the ones, obviously not the infinities. And it still does have inverse. So we can do secant to the negative 1 of x or arc secant. And the inverse restrictions are 0 to pi. So that's an example of the secant. All right, well, I'm going to backtrack right here. We are going to fix this because I didn't realize there's definitely a typo there. Because if it takes one hill and one valley to make a period of this graph, then if I'm starting at pi over 2, negative pi over 2 to pi over 2, that just gets the valley. And I need to go from negative pi over 2 to 3 pi over 2 to get the hill. So it's actually 1 period pi, 2 period, not period, 1 pi to get to here, 1 period. I can't talk. Excuse me, 1 pi to get to there. So the period here would be 2 pi over b, and our inverse restriction. All right, you guys, I am so sorry. In my mind, I jumped that I was looking at a different function, and I just didn't think it through. I was thinking in terms of pi, and I wasn't thinking in terms of restriction. So forgive me. I made you mark out something that should not have been marked out. My apologies. And we are restricting this from 0 to pi. So if you were putting a restriction mark on, it would look like this, just like we've talked about before. And where we can restrict and graph all of the inverse functions. Most of the time we use this more for solving. So I just wanted to make sure that we got this right after I made you mark out a perfectly good thing to have on your document. Okay, I will pay closer attention as we go through the next function that we're going to look at, which is going to be cosecant. Okay, so next one is cosecant. And so notice because cosecant is the reciprocal to sine, then like we did on the other graph, we're going to graph the sine function in the middle of our cosecant. So here is sine right here, the dotted line in the middle. So we're talking about just plain old sine that's oscillating between 1 and negative 1 going through this graph. And then everywhere that the sine graph is 0 would make its reciprocal graph undefined. So you can see that we have lots of asymptotes because there's lots of places that can happen. You're dealing with this periodic function. So here are all of our asymptotes that are occurring. And don't forget the one that's right here on the axis. And once again, we have pieces of the graph trapped between vertical asymptotes. So we have that. And then when we're looking at a period of cosecant, once again, it's going to be a hill or a valley. So we're looking at that going from here all the way over to here. So you're talking about this chunk of the graph right here, right here. That's the main way we can restrict that. And we're going to have one hill, one valley. Just like our last graph secant, we have the low points on the sine graph will be the high point or the top of the hill, and the top of our sine graph will be the bottom of the valley. And it once again takes one hill and one valley to make one period. So we have multiple asymptotes. We have things that we skip over those asymptotes, trap use in between, all of just very similar to what we had before. So remember that you're going to have vertical asymptotes when sine is 0 because it's a reciprocal function. That means you are going to have asymptotes at every 0 plus pi n. So the first one is here on the vertical axis, and then we have to add pi to get over to the next one. And so the k is just how many whole numbers are we going to add. The period for Cosecant is 2 pi also. So if you have a b value, you can take 2 pi divided by b to find the new period. The range is bouncing from negative infinity to the -1 down here and then up 1 to infinity this way, because remember you read it bottom to top. The inverse, we can still have arc cosecant, we can have cosecant to the -1, and its restriction is going to be from negative pi over 2 to pi over 2. So if you're thinking about a restriction mark on the axis, then we would go like, okay? So that's our cosecant graph. So now let's move and look at cotan. So the cotan graph looks very similar to the tangent graph. It is still a little wiggle. The vertical asymptotes that you're seeing are happening here and here and here. So it also has a vertical asymptote on the vertical axis. And the graph or period is trapped between the two vertical asymptotes. So that means one period is going to go from here to here. Just like when we did tangent, that wiggle was trapped between two vertical asymptotes. Notice that in tangent, it went from pi over 2, negative pi over 2 to pi over 2. So that wiggle actually went through the origin right here. Cosine starts at the vertical axis and then wiggles to the first asymptote over here at pi. So there are some differences. In this case, cotangent, it's a vertical asymptote and it occurs when sine is equal to 0, because in this case, I'm thinking about, remember, cotangent of x, and that's cosine of x over sine of x. Okay, so that's why we're using this one. And so we know we're going to have vertical asymptotes at when this bottom of my fraction is equal to 0, because that first vertical asymptote is happening at 0, then the equation for the vertical asymptotes would be x equals 0 plus pi k. The period, like tangent, is only pi. So if we had a b value, we would take pi and divide it by b. The range is going... Okay, let's backtrack on the range, because the range is bottom to top. So go ahead and get rid of that, because that's definitely a typo on my part. And we're going to go from negative infinity to positive infinity on the range, because you just start low, go high, and there's no breaks in it. So if we were looking, at the domain, then we would go from vertical asymptote to vertical asymptote. So as we're looking at the inverse, so the inverse is still going to be cotan to the -1 of x, or arc cotan of x. And the restriction, so if we were doing inverse trig, the inverse trig restriction for cotangent would be 0 to pi. So our restriction mark on a graph like this one would look something like this. All right, so that goes through the basics of the three functions. And now we're going to use what we know about each function to answer a few questions, and then we will be through. We are going to do a little bit of calculator practice at the very end, but we're going to go through and make sure we can answer questions about vertical asymptotes and range and things like that. Okay, so for example 1, we can see that we have a function here. It's asking us which of the following is a vertical asymptote. So there's a couple of ways we can approach this. When we look at the function itself, we know it's had a vertical dilation by 3. And then we have some horizontal stuff going in here because we have some frequency there. So basically the way that I would deal with finding vertical asymptotes is I would make sure I remember that secant of 2x is the same thing as 1 over cosine of 2x. So when secant of 2x has a vertical asymptote, it's going to have it when the cosine of 2x equals 0. So we have a couple of ways that we can find that. We can use the vertical asymptote equation, and adjust for that 2x right there. So we can say 2x equals pi over 2 plus pi k. And then we can simply adjust for the 2. So to get rid of the 2, I'm going to multiply the equation through by 1/2. So that's going to be x equals pi over 4 plus pi over 2k. And so then I could see the first asymptote is going to be at pi over 4, which is going to be answer choice C. We could also think about where the first answer choice is, or where the answer choice is. So what I would think about is the first VA is at pi over 2. So then we're going to take 1/2 of pi over 2, and that would give us pi over 4. And so we can see by just calculating the individual vertical asymptote, we could get to our answer that way, or by adjusting the equation, which would allow us to get to our answer that way. Okay, so the next one is the same type of question. So here is the function. Here it's asking for vertical asymptote. So go ahead and pause your video and work through that one. This time it's the cosecant function. So remember that we're thinking cosecant of pi x equals 1 over sine of pi x. And so we're looking at the sine function has a vertical asymptote when sine of pi x equals 0. So sine of pi x, let me rephrase that real quick. And that is really going to be cosecant of pi x has a VA when sine of pi x equals 0. Okay, so pause your video. Pick one of these two methods to solve for your answer. Pause now. Okay, so if you did the equation for the asymptote would be pi x equals pi k. Then we would multiply by 1 over pi to get rid of that pi that's right there with the x. And so I end up with x equals k. So x equals a constant. So I could see and kind of look up here and maybe narrow it down. Or if I knew that that first vertical asymptote is at pi, then I can take 1 over, like the reciprocal of the b, so 1 over b, and figure out that that was actually at 1. And so in that case, it was made it a little bit easier using that method. All right, the next one, example 3. Example 3 gives us the equation h of theta. So we have 3 cosecant theta over 2, and it wants to know which one gives us the range. So what we want to start with thinking is, what's the range of sine of x? So hopefully we remember it goes from -1 to 1. It bounces between the highs and the lows. And so then I want to think about what is the range for, and it is cosecant. So cosecant. So remember that goes from -infinity to -1, and then skipping up to the 1 and going on to -infinity. So basically what we're thinking about here is, what's this transformation 3 doing to my graph? And we know that that's a vertical dilation of 3. So we know that that's going to change the range, right, of my function. So then, therefore, the range of h of x equals 3 cosecant theta over 2 has been vertically stretched to go up to +3 and down to -3. So that's now going to go from -infinity to -3 and then jump up to the 3 to infinity at the top. Okay, so that's just adjusting and thinking about this, how this piece right here, that vertical dilation is going to affect the range, or how those two hills and valleys are going to separate further from each other. The middle of the graph is between the two, between the hills and the valleys, just not physically on the graph, but in the middle of them. Okay, example 4 is what we did a moment ago. So we have this equation, we have this vertical asymptote that we're looking for, and we want to know which one's the same. So pick one of the methods, either with the equation or with just finding the asymptote, and you can go from there. And this time we're using cotangent. So as we do cotangent, remember we would be thinking cotangent of 2 pi x would be equivalent to the reciprocal, or 1 over tangent of 2 pi x. Remember that that vertical stretch is not going to change anything in terms of the function itself, just how far up or how far down it gets stretched. And because this is a wiggle graph, how much skinnier that wiggle is actually going to look like. All right, so you can either do it with the first asymptote and adjust that way, or you can do it with the asymptote equation and just that way. Pause your video. So in this example, we have the first vertical asymptote is at x equals 0, so it's on the vertical axis itself. The second vertical asymptote would have been at x equals pi. The -5 means it's a reflection over the x-axis and then a vertical dilation by 5. And then that 2 pi, remember that's all a constant, and the x is the variable. So if you're setting up the equation, you do 2 pi x equals the equation of the asymptote, and then that means you have to multiply by the reciprocal of this piece, which is 1 over 2 pi. So we could end up with this, or we could end up with this. If we calculated the first one here, I would go with this first one right here, pi, and then do 1 over 2 pi to help narrow down your answer choice. And so then we can see that it should be B. Okay, so now we're moving into solving involving secant, cosecant, and cotangent. We're going to do it very similarly to the way that we solved equations for sine, cosine, and tangent. We are going to do just that we did before. So we're going to isolate that trig function in the equation, and then we're going to use the reciprocal properties to be able to get to our answers. And this is going to allow us to keep using prior knowledge as we work through a problem. All right, so let's do this first read together. So we see we have f of x, we have g of x. They are x coordinates, so I'm combining my first and second reads together here for you guys. So that's going to be equivalent to x equal. The point of intersection, that means I need to know when f of x equals g of x. Of the graph of f and g, and then we have this restriction here. And when we have a restriction written like that, we know that our answers are going to be a list. Okay, so we're not going to have to write equation answers. So the first thing that we do here is we need to apply the rule that we're using, which is f of x equals g of x. So I'm going to go ahead and write that down so we don't lose sight of what we're trying to do. F of x is 4 cosecant x and plus 3. And then g of x is 11, so we're setting that equal to 11. So pause your video and isolate your trig function. Okay, so now that we have that isolated, let's think what this means. Remember that we're using cosecant of x is 1 over sine x. All right, so what does that mean? That means cosecant of x, let's make it a fraction, 2 over 1. And what can we do with fractions when we want to do the reciprocal? Then we can say sine of x is, and we can turn this upside down and make it 2 over 1. So I'm not 2 over 1, excuse me, turn it upside down, and then I just rewrote it again, didn't I, guys? So then it's 1 over 2. So we can use that idea of reciprocal to move us into the problem. So here's what I'm trying to solve. Sine of x equals 1/2. So I should be able to do this without much difficulty. I know that sine is positive in the first and the second quadrant. I know the angle in the first quadrant that has a sine value of 1/2 is pi over 6. And I know the angle in the second quadrant that has a sine value of 1/2 is 5 pi over 6. So what that restriction right here means is that if we're starting here, we're going all the way around and stopping right there at 2 pi. So that's one rotation around. The restriction, I'm just writing this in our notes so that you have it. It's me 0 less than or equal to x, which is less than 2 pi. So we would not include 2 pi if that were a possibility. And we said that our answers were going to be in a list when we have that restriction. So our list is simply going to be x, because that's our unknown in the equation, equals pi over 6 and 5 pi over 6. All right, so C using what we already know. So it was a matter of isolating the trig function, thinking about the reciprocal identity that we could use, setting my value up if it's not a fraction as a fraction, so that when I invert it to get my reciprocal of the fraction for my reciprocal identity, it makes it very easy to do. Okay, so let's read the next one. So we have a function h and we have a function k. We want the x coordinate. So once again, we're looking for x equals of the points of intersection. And so points of intersection mean that we need to know when h of x equals k of x. And we have a restriction here from 0 to 2 pi. So our answers are going to be in a list. So we read it the first time to make sure we understood the problem. And then we identified the pieces in the problem that are important. That's our second read. That's when we enter the problem. And now we're going to proceed to solve the problem and check and make sure our answers make sense. So what is it we're trying to find? We're trying to find h of x equals k of x. And so that means my h of x is 3 minus 1/2 secant of x, and that's going to equal 4. So step one, solve and isolate your trig function. Pause your video and take care of that. All right, so hopefully you were able to do that without too much trouble. So remember what we learned today is secant of x is 1 over cosine of x. So I'm going to say secant of x is, and I'm going to take this secant that we found, I'm going to say negative 2 over 1 because it's easier if it's a fraction. And then its reciprocal is cosine of x. So I can turn the fraction upside down. I'm going to get negative 1 over 2. And so that's what I'm going to solve. So I'm going to solve cosine of x equals negative 1/2. Remember, within one rotation around the circle. So go ahead and find your solutions. Pause your video now. All right, so we know cosine is negative in quadrant 2 and quadrant 3. So the angle in quadrant 2 that has a cosine value of negative 1/2 is 2 pi over 3, and the cosine, or excuse me, the angle in quadrant 3 that has a cosine value of negative 1/2 is 4 pi over 3. And so since that's within our one rotation and our problem set up here says give me a list of answers, then my answers are 2 pi over 3 and 4 pi over 3. Does the form of my answer make sense? Yep, because it told me it was restricting it right here. And that is where I knew when I did my second read that my answers were going to be in the form of a list. All right, so the next problems are calculator driven. So if you don't have your calculator with you right now, pause your video, run and grab that, and then we're going to look at the last two examples and practice some calculator skills. Okay, so first thing that we want to make sure is that we are in the right mode in our calculator, and that should be radians. If you reset your calculator, it automatically puts you in radians, but if you've been doing other things on your calculator, then you should always double check and make sure that the radians is highlighted right here and not the degree. So all of these problems in example 7 are going to use the calculator and you're going to be typing directly in your home screen. So notice there is no button here that says arc anything on the calculator, right? It's only arc sine, arc cosine, and arc tangent. So we're going to use those. So we're going to go through these problems A through G and set them up. Then I'll have you pause your video and go ahead and practice punching them in so you can make sure that you can do that part of this correctly. All right, so let's go through the setup and then we'll pause. So on the first one, arctan means we're going to be doing tan to the negative 1 of 4.84. So that one should be fairly easy to enter in the calculator. Right here, arc cosine, so that would be cosine negative 1 of negative 0.349. Sine to the negative 1 of that, that's a punch in, so you can do that one. Tangent, then we're going to do the tangent function. We're going to get the fraction template and type in 2 pi over 9. So that's a direct punch in, so that shouldn't be any trouble. Cosecant, well, we don't have cosecant, but what's the reciprocal, excuse me, for cosecant? That's sine. So I'm going to do 1 over sine of 16 pi over 9. And then secant, we don't have a direct punch in for that one. So what's its reciprocal? The reciprocal of secant is cosine. So we're going to enter 1 over cosine of negative 4.3. And then cotangent, again, we don't have the cotangent button. So we're going to use 1 over tangent of 2.5. All right, so now you know how to punch them in your calculator. So I want you to go ahead and do that and approximate your answers to 3 decimal places, just like we should be practicing for all of our AP level classes, all to 3 decimal places. All right, pause your video. How you did on the first part. We entered those in. We've got approximately 0.839 here. We used our reciprocals here as we set up, and we got those answers. All right, let's look at the last problem. Again, we're going to do this with a calculator. There are some techniques that I want to show you when it comes to doing bigger problems with a calculator. But today we're just going to focus on, what and the restriction with the restrictions, getting the information into Desmos and seeing what this would look like. So as we did our first read through the problem, and then I did my second read here. So we have our equation. We know we're going to need x equals a point of intersection where p of x equals 2. So where this equals 2, and we have a restriction. So as we go through the steps for a problem like this in Desmos, the first thing that we're going to do, and I'm going to line the steps out and talk through them, and then I'll let you pause your video and try it. And then I will show you my Desmos so we can make sure everybody's good to go. So we would put in an equation in this form, 3 minus 1.7 cotan of 0.5 x minus 1. And then we would add a second equation where we're going to have p of x equals 2. Then I would probably at this point go back to the first equation. And so if you go to the little wrench icon, you can do your step to be pi. And so we're talking about the first equation. And then once we have that in, we can adjust our graph to the restriction. That way we can see from the 0 to 2 pi. That's really easy to do in Desmos. You just move the graph around and zoom in. And then we're going to mark the intersections. And finally, check the answers that are within my restriction. And that's important because remember, these are periodic functions, so they go on forever. So you may see more intersections that actually apply to the problem themselves. So go ahead and call up your Desmos, and I will switch my view so that you can see mine. Okay, so if you followed your steps, hopefully you will have the same thing as I do once I follow my steps. So I'm going to say P of X equals, and then I'm going to put in 3 minus 1.7, and then I have cotan of 0.5, or let's go ahead and put a 4 in there, 0.5x minus 1. And then I'm going to add another equation, and I'm going to put in P of X. Oops, hit a couple of letters there. P of X equals 2. And so now I can see the wiggle graph of my cotant, and I can see that. If I go up here to my little wrench, then I can step in here and make sure that that first equation has a step of pi and it's in radians. And then I can move once I'm in here, I can move my graph over. So I'm seeing, the part of the graph that I want, which is going from 0, and we can see 2 pi right here. So notice you can see how many times the black graph crosses the red line. And so I want to mark right here, right there, which is before 2 pi. And you can see the next intersection is back here after 2 pi. So then what I just found very easily with using my Desmos was that my x equals is approximately 4.078. So we would go out 3 decimal places. And so then I can see my answer here. So you could do, in theory, you could do these kind of problems on the calculator by isolating and getting x by itself, but we do have to be a little careful with how we do that when we're using reciprocal notation, and then sometimes we have to use inverse notation. So we will do more of that, but for now, this was just a kind of introduction or practice and making sure we could use those Desmos tools. All right, guys, do your daily practice, and I'll see you next time. Thanks. Bye.